Hello everyone, welcome to Learn Wireless Technology. In this tutorial, we will discuss the LTE resource grid. This is a very important topic as it covers some of the important concepts of physical layer in LTE. It explains what are the major elements involved in carrying the data over the air. We will see what exactly it is that a user is allocated so that it is able to send or receive data over the radio interface. We will discuss what are resource blocks, resource elements, how a data carrying element can be viewed in time and frequency domain, what are antenna ports. Now the concept of antenna ports is a little confusing topic among many people, which is explained very well in this video. So after watching this tutorial, you will get a very good understanding of the physical layer and what role it plays for transmitting any data. So please watch the video till the end. Since physical layer is a very vast concept, I've tried to cover maximum topics and so the video would be a little lengthy. If you want to jump directly to a particular topic, then you can click on the timestamp provided in the video description. But it is recommended that you watch the complete video in proper order to clearly understand the topic. So let's start. So when we talk about resource allocation to UV for uplink data transmission, or when we talk about downlink data transmission from E node B, we are basically talking about resources that are involved for transferring the data over the air. So what exactly are these resources? We know that the actual data that is transmitted over the air is carried by an analog signal, which we call it as an OFDM signal in LTE. So before this OFDM signal is generated at the transmitter end, the data goes through multiple physical layer processes. And one of the process is mapping the data bits to something called resource blocks. Resource blocks are the actual data-bearing entity or element that is allocated for a user based on the amount of data to be transmitted and bandwidth requirement. So any resource block can be viewed in two domains, that is frequency domain and time domain. Let's have a look at the frequency domain organization of resources. This is the frequency axis. And these are the closely spaced waveforms known as orthogonal subcarriers, which are present in frequency domain. LTE uses these orthogonal subcarriers to transmit user data, control information, or reference signals over the air interface. This region here is referred as a resource block. This is just a frequency domain view of a resource block. As you can see, the resource block contains 12 subcarriers, and the spacing between two consecutive subcarriers is 15 kHz for normal operation. With 12 subcarriers and 15 kHz spacing between them, a resource block occupies 180 kHz of bandwidth. 12 times 15 kHz equals 180 kHz. In OFDMA, different subcarriers can be used for different users. Now the reason for using orthogonal subcarriers is that they provide the facility to have tightly packed waveforms without causing any interference. Even though the waveforms are closely spaced, the orthogonality exists between them, which means when the signal is at its peak amplitude at any point, the other signals are zero. Due to this, the intercarrier interference is eliminated and it saves a lot of bandwidth. I've explained the concept of OFDM in detail in another tutorial. You can check that. Now if you see here, there's a small gap between the two subcarriers. This is called as DC subcarrier or direct current subcarrier. It is available at the center of the frequency band and has no energy. The DC subcarrier is used by the UV to locate the center of frequency band. And these are the two guard bands at the edge of frequency band. The guard bands are present to avoid any interference with the adjacent bands. The subcarriers in the guard band does not perform any RF transmission. So this is the overall frequency domain representation of a resource grid over a channel bandwidth. Let's have a look at some of the important parameters in frequency domain. This table provides the important frequency domain parameters with respect to different channel bandwidths. The first row here shows the different channel bandwidths on which LTE can be operated. The minimum bandwidth is 1.4 MHz and maximum is 20 MHz. This row shows the number of subcarriers that can be used in a particular channel bandwidth. Now the number of subcarriers mentioned here contains a DC subcarrier as well. DC subcarrier, as we discussed before, does not contain any information. It does not have any energy. It is just used by the UV to identify the center of the bandwidth. So the actual number of subcarriers that carry the data is the number mentioned here minus 1. So for 1.4 MHz bandwidth, we have 72 subcarriers excluding the DC subcarrier. For 3 MHz, we have 180 subcarriers. For 5 MHz, we have 300 subcarriers, and so on. The maximum subcarriers that we can have is 1200 in case of 20 MHz channel bandwidth. Out of this total subcarriers for each channel bandwidth, we also have few subcarriers allocated for guard band. Guard band or guard carriers occupy around 10% of the total bandwidth. This row gives the FFT size which are used during signal processing. FFT size is nothing but the number of subcarrier inputs to FFT or IFFT. The value of FFT size is applied to the calculation used for transforming time domain symbols into frequency domain using fast Fourier transform. In time domain, the data bits are modulated and mapped to OFDM symbols, and these OFDM symbols are transformed into frequency domain points which are then mapped onto the subcarriers. The FFT size varies with the channel bandwidth. It ranges from 128 to 2048. Where 2048 is the maximum FFT size for 20 MHz bandwidth. Now the sampling rate or sampling frequency is calculated using the subcarrier spacing, that is delta F, and FFT size, that is N. The value of sampling rate here are represented in megahertz. Now if you take a look at these values, they are the multiples of UMTS sampling rate, which is 3.84 MHz. Take the first example of 1.4 MHz bandwidth. The sampling rate is 1.92 MHz, which is half of 3.84. For 5 MHz bandwidth, the sampling rate is 7.68 MHz, which is 2 times of 3.84. For 10 MHz, the sampling rate is 15.36 MHz, which is 4 times 3.84. For 15 MHz, it is 23.04 MHz, which is 6 times 3.84, and finally for 20 MHz the sampling rate is 8 times the UMTS sampling rate, that is 30.72 MHz. Now in LTE, the reason for choosing the sampling frequency as multiples of UMTS sampling frequency is to allow for smooth handover between LTE and UMTS. And these are the number of resource blocks that can be allocated to users. The number of resource blocks depends on channel bandwidth. If you want to calculate the number of resource blocks in a bandwidth, then you can do it easily. You just need to divide the total number of subcarriers by 12, because 12 subcarriers form one resource block. Say for example, we have 300 subcarriers in 5 MHz bandwidth. Please note that we are not considering the one DC subcarrier from this, because it is not used for carrying any information. Hence we consider just 300 subcarriers. So if we divide 300 by 12, then we have 25 resource blocks. Similarly, for 20 MHz bandwidth, we have 100 resource blocks. Now the resource blocks that we are talking about are the subcarriers in frequency domain allocated to user for signaling purpose or for data transfer. Meaning that these resource blocks or the subcarriers in it are the actual usable resources. And these resources or subcarriers constitute 90% of the bandwidth. If you take a look at this row, it shows how much bandwidth is occupied for allocation to a user. Consider this 20 MHz bandwidth. Here approximately 18 MHz of bandwidth is usable and can be scheduled for a user. This is because the remaining 10% is used as guard band to avoid interference with adjacent band. So the downlink bandwidth efficiency is 90% for all the bandwidths except for 1.4 MHz. It has only 77% of efficiency and rest of the bandwidth is used as a guard band. Now if you notice here for 20 MHz channel bandwidth, the usable bandwidth is 90%, which comes to exactly 18 MHz. But here we have 18.015 MHz. So from where this additional bandwidth occupancy of 15 kHz is coming from? We know that each subcarrier holds 15 kHz bandwidth, and this additional 15 kHz bandwidth is coming from the DC subcarrier, which is not used for data transmission, which is also taken into account. Similarly, for all other bandwidth configurations, we have this DC subcarrier frequency accounted for occupied channel bandwidth. Now let's look at the time domain organization of a resource grid. The resources are represented in terms of radio frames in time domain. We already discussed in brief about radio frames and their types in earlier tutorial. We will discuss some additional details here. A radio frame is 10 milliseconds long and consists of 10 subframes of 1 millisecond each. Each subframe is further divided into 2 time slots of 0.5 milliseconds each. A time slot contains 7 OFDM symbols when normal cyclic prefix is used and 6 OFDM symbols when extended cyclic prefix is used. Now if you see here in LTE, different time intervals or different fields in time domain are expressed in multiples of a basic time unit, that is TS. As you can see here, the radio frame duration is expressed as T frame, which is equal to 307200 multiplied by TS. Similarly, the subframe duration T subframe is expressed as 30720 multiplied by TS. And the slot duration T slot is expressed as 15360 multiplied by TS. So likewise, any field in time domain can be expressed using this basic unit TS. Now TS is equal to 1 divided by 15,000 cross 2048. This value is expressed in seconds. Here 15,000 is nothing but the 15 kHz subcarrier spacing, and 2048 is the FFT size of system bandwidth of 20 MHz. The value of TS comes to approximately 32.6 nanoseconds. Now coming to this number here, 307200, it's a number of samples in a radio frame of 10 milliseconds. Let's see how this number came out. We know that the sampling rate for a 20 MHz channel bandwidth is 30.72 MHz. That is 30.72 million samples per second. So to calculate the samples per 10 milliseconds, that is per radio frame, we need to divide 30.72 million by 100, because in 1 second we have 100 radio frames. We can apply similar calculation to other fields as well, such as subframes and time slots. So we can say that the time interval between two samples is 32.6 nanoseconds. Now coming to these OFDM symbols, considering this scenario as a normal operation, a slot is divided into 7 symbols. Each symbol is preceded by a cyclic prefix. The cyclic prefix for the first symbol has a slightly longer duration compared to the other cyclic prefixes. The first cyclic prefix has a duration of 5.2 microseconds with 160 samples, while other 6 cyclic prefixes have a duration of 4.7 microseconds with 144 samples each. The useful symbol region over here is of 66.7 microsecond duration and 2048 samples. This is the region which contains the actual data bits. In case of extended mode, the number of symbols in a slot is 6 and the duration of cyclic prefix is a bit longer compared to normal mode. Normal cyclic prefix is used in high data rate applications, while extended cyclic prefix is used in MBMS applications. Now let's go through some resource grid definitions. We discussed how a resource is viewed in time and frequency domain. We talked about subcarriers in frequency domain and OFDM symbols in time domain. Let's see how these resources can be further magnified and what is the smallest element in a resource grid that can be realized. So this is how a resource grid is represented for easy understanding. Let's see how this resource grid diagram can be described. What are the different terms used here, and we'll see how we can relate this to what we discussed so far in this tutorial. So the signal that is transmitted over the air carrying data is nothing but a set of resources, and a resource grid is a set of these resources viewed in time frequency domain. If you see in this diagram, the complete resource grid is a magnified view of one time slot. The vertical axis is the frequency domain which contains the subcarriers, and the horizontal axis is the time domain that contains OFDM symbols. A resource grid can be represented in frequency domain as the product of NRB power DL and NSC power RB, where NRB power DL is the total number of resource blocks in the downlink direction and NSC power RB is the number of subcarriers in one resource block. As you can see in this diagram, this is the frequency domain representation where the downlink resource blocks spread through the entire channel bandwidth in vertical axis. And this is one resource block and the subcarriers contained in it. Please note that the concept here applies for both downlink and uplink transmission, but for explanation purpose, I have mentioned only about downlink direction. Now, in time domain, the resource grid is simply represented as the number of OFDM symbols denoted by nSym that spreads across the horizontal axis. The number of downlink resource blocks, that is nRB power DL, depends on channel bandwidth. The minimum resource block is 6 for bandwidth of 1.4 MHz and maximum resource block is 100 for 20 MHz bandwidth. NSC power RB is the number of subcarriers in a resource block. nSym is the number of OFDM symbols. The number of OFDM symbols depends on cyclic prefix and subcarrier spacing. Now the smallest unit in the time frequency grid, as you can see here, is called as resource element. A resource element is nothing but a subcarrier in frequency domain and an OFDM symbol in time domain. And a set of resource elements is called as resource block, which is assigned to a user for data transmission. We will discuss more about resource elements and resource blocks in the coming slides. Resource element, as we understood, is the smallest unit in the time frequency resource grid. It corresponds to a single subcarrier assignment for a single symbol duration. So all these small squares in the entire grid are resource elements. Now there are few additional terms that are derived from resource elements, which is also important to understand. First is resource element group, or REG. It is a group of 4 or 6 resource elements. These group of resource elements are assigned to specific control channels that are used to carry control information. The region highlighted with red border is the resource element group. As you can see here, there are 4 usable resource elements in a group. The group of 6 resource elements shown here will also have 4 usable resource elements. The other 2 resource elements are assigned for downlink reference signals. Reference signals will have some other purpose, they don't carry any control information. Now a group of 9 resource element group form a control channel element. The region highlighted with brown border is the control channel element, or CCE. It is used for PDCCH signaling, that is, the region is assigned to PDCCH channels to perform control or signaling procedures for downlink transmission. One CCE contains 36 usable resource elements for control information. Now the control region is usually present in the first time slot of a subframe. The control region occupies the first 3 symbols in case of larger bandwidth, while it occupies the first 4 symbols in case of smaller bandwidths. Next, coming to the resource blocks, we already discussed about this many times throughout this tutorial. Let's quickly go through some additional details. Resource block, as you know, is a set of resource elements that consists of 12 subcarriers for a duration of a time slot, which is assigned to user for uplink and downlink transmission. With 15 kHz spacing between 2 consecutive subcarriers, a resource block occupies 180 kHz in frequency domain. In time domain, it spans for a duration of 0.5 millisecond or 7 OFDM symbols. Resource blocks can be of different types depending on the cyclic prefix used and the subcarrier spacing. Let's have a look at each of them. This is an example of a resource block with normal cyclic prefix having 7 OFDM symbols in time domain and 12 subcarriers in frequency domain. There are total 84 resource elements in this resource block. This is an example of a resource block with extended cyclic prefix where there are 6 OFDM symbols in time domain and 12 subcarriers in frequency domain. In the third type, the subcarrier spacing is 7.5 kHz and only 3 OFDM symbols. These type of resource blocks are used for MBMS applications. The number of resource blocks in a resource grid depends on channel bandwidth. Higher the channel bandwidth, more will be the resource blocks. Now moving on to the next topic, that is antenna ports. Now this is quite a tricky concept that creates a lot of confusion. When people hear about antenna ports, they start imagining about the antenna ports present in the transmitting or receiving entity, that is actually responsible for transferring data over the air, like the physical transmit antenna present in E node B or UE. But that is not the case here. The antenna ports that we are talking about is not the physical antenna, but it is a logical concept. It simply means that antenna port is not same as physical transmit antenna. Antenna ports are the logical entities that are distinguished by their reference signal sequence. It means that an antenna port is defined by its associated reference signal. Say for example, antenna port 0 is associated with cell-specific reference signals. Antenna port 5 is associated with UE-specific reference signals. Let's take a look at this set of resource blocks. It has a specific arrangement of reference signals at various resource elements. As you can see here, the location of reference signals is denoted by this dark color. Now these reference signals are cell-specific reference signals. It is referred as antenna port 0, which contains cell-specific reference signals with one antenna configuration. There can be various antenna configurations such as 2 antennas, 4 antennas, where the reference signals arrangement are different and they are referred as antenna port 1, antenna port 2 and antenna port 3. Hence, port 0 to port 3 are indicated by the existence of cell-specific reference signals. Each cell-specific reference signal antenna port is transmitted on a separate physical antenna to create spatial diversity in the radio transmission path. Similarly, when the resource elements contain UE-specific reference signals, they are referred as antenna port 5 or antenna port 7 to 14 based on the arrangements of reference signals in resource elements. Such antenna ports are used for different downlink transmission schemes such as spatial multiplexing, transmit diversity, beamforming, etc. If you know about the types of reference signals and its uses in LTE, then maybe you can understand this concept better. We will discuss about reference signals in coming tutorials. Different antenna ports are mapped onto physical transmit antennas or antenna elements, similar to how data bits are mapped onto different resource elements. The mapping can be 1-to-1, 1-to-many, many-to-many, or many-to-one. Also, multiple antenna ports can be transmitted on a single physical transmit antenna, and a single antenna port can be transmitted on multiple physical antenna. Let's consider a case of 1-to-1 mapping between antenna port and physical transmit antenna, when the transmission is in downlink direction from E node B to UE. In this case, antenna port 0 is mapped to physical antenna element 0 and antenna port 1 is mapped to physical antenna element 1. Here each antenna port is associated with a cell-specific reference signal. When these transmissions arrive at UE, then the UE views these as two separate downlink transmissions from the network, one transmission from antenna port 0 and other from antenna port 1. Now, if you consider a case of one-to-many mapping where a single antenna port, say port 5, is mapped to 4 different physical transmit antenna elements. Here, UE views this transmission as a single downlink transmission from the network, even though 4 different physical antennas are used for transmission. Here, antenna port 5 is associated with a UE-specific reference signal. This particular case is used for the support of beamforming, where the transmission from multiple physical antennas are directed towards a single UE. So basically, from UE's perspective, antenna ports are viewed as virtual since they represent the downlink transmission rather than actual transmission from physical antennas. In this way, you can imagine number of possibilities of antenna ports mapping with physical transmit antennas depending on the purpose of transmission and the application. So with this we come to the end of this tutorial. I hope you understood the concept of resource grid in LTE, what are the different elements involved and what are antenna ports. Thanks for watching.